The second step is Ehrenfest theorem. Now, this theorem begins by us considering the time derivative of the average of an observable. And we're hoping at the end of the day, so I'll write it down here again, to find, we haven't proved this yet, that this is just the average of this interesting commutator with this prefactor 1 over I h bar. Now, to prove this, it's going to take a little bit of work, but we're going to just follow our mathematical logic through, kind of massaging the time derivative of this observable until we can get to an expression that looks like this. So let's begin. So the first thing I would like to note is that the average of an observable, you will notice, has nothing to do with variables like the position x, right? The position x has all been integrated out when we calculated the average position or the average momentum or the average of whatever observable. What's left then is just simply a function of time. And because it's only just a function of time, whether or not we write the total derivative or just the partial derivative with respect to time, it really makes no difference. We get exactly the same result and the same meaning. Now, continuing along with my train of logic here, let's write out what that average is. Well, mathematically speaking, we know how to compute it as the Hermitian inner product, right? This bracket notation of our current value for the wave function. So I might want to be a little explicit because this wave function depends on location and time. It gets starred, right? And then multiplied by the operator that corresponds to my observable acting on my wave function psi of x and t. That's the more compact notation. And because this is the first time we're kind of manipulating things in this notation, I'm going to do sort of a parallel proof where we will look actually at things in both notations. So this is just the same thing as the time derivative then of the integral over all x of the function in the bra side of my bracket, which is a psi star of x and t, multiplied then by my observable acting on psi of x and time t. Very good. Now, let's work through and think about taking this time derivative. And as I said, I'm going to play both notations off of each other because it's the first time we're doing this kind of thing. I'll do a lot of the grunt work really in the more familiar notation for the first time we're going through a derivation like this. So I'm going to draw a little line here down the center of the screen where we can do the proof sort of simultaneously in both notations. So let's think about our more traditional notation. Notice what I have here is the time derivative of an integral with respect to x. Very key is the fact that this x has nothing to do with the time derivative that I'm taking, right? This x is summed over all the different possible values of x, if I want to emphasize that there's an integral like this, right? It's just a dummy integration variable. In essence, what I have is an integral is basically a sum, right? So I've got a sum of a bunch of functions of time t, and I'm summing over this index x. So if I have a derivative of a sum over x, that is the same thing, of course, always as the sum of the derivatives. So I can replace this side then with what will equal then the sum, which will be minus integral minus infinity to infinity dx, then of the time derivative of the functions that appear inside of my integral. So there's psi star, which depends on x and t, right? There's times O hat, and then there's psi that depends on x and t. Now, the next step is we know how to take a derivative like this because I have a product. So I have the simple product rule. So that's integral minus infinity to infinity dx. And the product rule says I take the derivative of the first piece. So that's the time derivative of psi star, which does depend on time t. That's why I'm writing the derivative of that, right? I'm just trying to save myself a little bit of space by not writing the x and t so much. And then times, of course, the rest of the product, which is O, acting on psi of x and t. So there's going to be two terms, actually. Plus then the first term, psi star, times then the time derivative of the second term, which is the result of O acting on psi of x and time t. Okay, and then I have a closed bracket. Very good. Now, we can ask ourselves, what does this expression actually look like in our more familiar notation? So in the more familiar notation, right, notice I've got now a sum of two terms. Both of them are in the standard inner product form. There's just some, slight differences in the two pieces. Oh, and one thing I wanted to point out, and we've seen this kind of thing before. The term I just wrote down is the time derivative of psi star. But remember, that is the same thing as the star of the time derivative of psi, right? It was initially time derivative of psi star because that was the function which entered into the product rule. But then what I notice is the fact that, well, if I take the star of the time derivative of psi, because time differentiation has nothing to do with complex conjugation, that's the same thing as just the time derivative of psi star. Why I've made that slight maneuver is you'll notice now I've got two terms that are exactly in the form of the Hermitian inner product. So the first term is the time derivative of psi, which then gets starred and integrated against O acting on psi. And then I have a second piece, which is just psi inner product against the time derivative of the ket, basically. So that's the time derivative of O then acting on psi, like so. And because we haven't really finished thinking about this piece here, I'll write it out as psi of x and t. It doesn't really affect things much, but just want to be very explicit about things. Now, once you get used to this bracket notation, you will notice what we have here is really just a nice product rule for brackets, right? I get that the time derivative of this bracket, right, has two terms, and the two terms are first the time derivative happens on the bra, right? And then I just have my ket, and then I have the bra with the time derivative of the ket, right? It's a product rule, works directly for bracket. So after you gain some experience, you'll be able to go directly from this expression to this expression, saving yourself a lot of writing and thinking and steps. Okay, now, we have another thing that we would like to consider. The first thing I guess I should point out is I really like this term, the time derivative of psi, because I can relate that to the Hamiltonian of the system very quickly with the time-dependent Schrodinger equation. And then I'll have a Hamiltonian over here, I'll have an H and an O. It's starting to feel like where I'm trying to get. On this side, though, I don't have a time derivative of psi. I have a time derivative of an operator applied to psi. I want to think about that a little more, see if I can make some progress on that, potentially even, simplify it a little bit. So let's think about that. And let's think on this side where I've got sort of the more familiar notation. Let's think, well, what do we really mean by the time derivative of something? Well, a time derivative is in essence just a subtraction, right? What this is, if I write it out literally, it's the operator acting on psi at a slightly later time at t plus dt, and then I subtract off the same operator acting on psi at time t, right, because that's O at time t, acting on psi, right, and then divide it by dt. Now, something I'd like you to notice about our operators that we've been working with are in a form that are known as linear operators. I refer you to the class notes where you can see general proofs of this type of a thing. But a linear operator has the nice feature that the operator acting on a sum or difference of functions is the same thing as the sum or difference of the operator acting on the functions. In other words, I can basically pull the operator O out of this difference. And if you have any doubts on that, just remember some of our example operators, right? For the position representation, x hat, that is just multiplication by the number x. And since multiplication by x obeys the distributive property, then certainly the operator will also obey this nice property that I'm talking about. The derivative operator, which is closely tied, of course, to the momentum operator, which is just it's h bar on I times the derivative with respect to x also has the property that the derivative of a sum is the sum of the derivatives. Finally, notice that I can also pull constants in and out of a linear operator, right? I can have x times the constant times a function, or the constant times x times the function. It will be the same thing. And likewise, the derivative of a constant times a function is just the constant times the derivative of the function. So long story short, for any physical operator, they all obey this linearity property. That I can simply pull out the operator O and write it in this new form, where all of the action that has to do with taking a derivative, this is psi of x and t, divided by dt. All of that action happens now inside my operator, and hopefully now you recognize that this quantity here is really nothing other than the derivative of psi with respect to t. So this becomes O hat times the time derivative of psi is what actually goes into this term. So let's write this all out now in our more compact notation. So I'm going to have here, and kind of rewrite things more neatly, time derivative of psi on the bra. In the ket, I've got the operator acting on psi. For the second term, I have psi, and then my time derivative has now just moved past my operator, acting then on psi. Now, a quick way that we could have seen this a bit more directly would be if we had noticed, oh, excuse me, I don't want this thing here. I guess I have to do an escape. Control escape. I don't see it. I'm sorry. So the way we could have seen this a little more quickly if we were going through our more formal type derivation is we would look at this and say, okay, time derivative is just a difference. And a difference of an operator acting on a function is the same thing as the operator acting on the difference between the functions. So you would be able to make this maneuver here very quickly. Now, once I have it like so, I think I will rewrite it in the traditional notation one last time. So remember, I've got integral over all x. I have two terms now. I have the time derivative of psi, complex conjugated, and then I have O psi, right? Plus then, I've got psi star O acting on the time derivative of my wave function psi. Now, this is the stage where we can use, finally, the time-dependent Schrodinger equation. We know that the time derivative of psi from the time-dependent Schrodinger equation, which we had here at the very top, right? The time derivative of psi is just the Hamiltonian acting on psi divided by this prefactor of I h bar. So this will all become then the Hamiltonian acting on psi divided by this one factor of I h bar. And likewise, this time derivative will be the Hamiltonian acting on psi divided by this one factor of I times h bar. And I can, of course, make the same substitutions here, which I will do because I want to think about the math one last step here. And on this one, this will be replaced by Hamiltonian psi divided by I h bar. Now, the point I'm trying to make by writing this out so explicitly in our more traditional side is I want you to notice that now I have an overall factor of 1 over I h bar that I can pull out of my integral. So I'll pull that out. Now the only tricky part in pulling that out, of course, is that when I do so, I want you to notice that in this term, because it's complex conjugated, that I term, that picks up a minus sign. So what I actually have here is minus, and what's left inside that bracket is h psi, right? And then that whole thing gets starred still. It's all, the rest of it is inside the star. O acting on psi, plus then I've got now psi star O h psi, like so. So the only trick really in pulling out this IH bar is you have to remember if it's on the bra side, right, it comes out with a minus sign if there was an I there. So at the end of the day, I've got 1 over IH bar, and then I have a difference between these two terms, d by dt of psi. Oh, I'm sorry. It's h hat times psi, right? Because I'm using this substitution, O acting on psi, plus then psi with O acting on H acting on psi, where the IH bar has been, appropriately factored out like so. So now you can see we're making a lot of progress. I've got two terms here that look very much like the kind of thing that I would want, right? I'm hoping to get this funny commutator, right? I'm hoping to get OH acting on psi and then HO acting on psi with some kind of a minus sign, right? In fact, let's write down the kind of thing we're hoping for here. This would be psi integrated against 1 over IH bar. And here I'll write it all out. I want OH acting on psi and then subtract off HO all acting on psi. I'm hoping for something like this. And I almost have it. I've got the OH psi and psi, just like I have here. Psi, I've got the OH psi. I even have the 1 over IH bar. But then I need a minus HO psi. But I don't quite have that because the H here is on the wrong side. It's on the bra, and I need it in the ket. But fortunately, we have a very important property for all physical observables, namely that their operators are always, remember what we had called Hermitian. So I can always move this H from the bra side over to the ket side. So let's make that maneuver. Now that's one maneuver that's actually more clearly seen in the more formal bracket notation. So this will become minus now psi, and when the H comes over, it acts on whatever was on the ket side. So it's actually acting on what's already here, which is the result of O acting on psi. So I now have this replacement that I can make on this side. And then finally, if I try to write what I have now in the more traditional notation, just so you can see how we can now combine things, what I have is a 1 over IH bar integral dx, right? This this H now has moved over to here right before the O, so I've got a psi star. And what I want you to notice is I've got the same factor of psi star for both terms, so I can factor that psi star out. So it'll factor out like so. What I'm left with then is my minus sign, so I'll have then minus HO psi, because my H moves just before the O, plus then, over here, I've factored out the psi star, I have OH psi. So the long and short of it is, now that I have just psi in my bra side, I can combine them into a single inner product. So I will then have now 1 over IH bar, a single inner product psi, and then my two terms, so we just learned a new rule how to combine these. My two terms then are going to be O acting on H acting on psi, but I can factor that out as an operator, minus then H acting on O, then applied to psi, like so. And then finally now you can see this is exactly what we wanted to prove. This is psi. This constant IH, right, whether it's multiplying psi here or is outside my integral, it's easy to bring that in. So it also, I'm just bringing this constant into here. There's no minus sign trick because it's not on the bra side. So I can bring in the 1 over IH bar. And then this difference of operators applied in different orders is, of course, exactly the definition of my commutator. And that is precisely what we wanted to prove. That's exactly QED, quodata demonstratum. That is what we wanted to prove. This is exactly Ehrenfest theorem proved. So that is a very good, happy result.